So yesterday we briefly talked about this problem, the forward kinematics of 6-axis articulated robot Intelli-X, and the first part, as I mentioned, we were to assign the coordinate frame. So we saw that there are, a 6-axis robot, so you will be able to identify L0 to L6 as the coordinate axis. Recording is going on. So we first assign the coordinate frame Z L0, and then we will have L1. So L1 is a shoulder roll. So we will have this as the Z axis. That is your Z1, and then you can have Z2 in this direction or in this direction, whatever the direction you choose. So if I choose this direction, it will be Z2. Then you have 3, 4. And Z5 is the tool roll, so it will be like this, same origin, and finally you have Z6. So you can identify all those joint axes. Nobody is there? Just call him. So this way you can identify all the joint axes, and once you have the joint axis, then you assign the x-axis. X-axis should be normal to identify the origin first. Origin will be the intersection of both the z-axis, z1 and z0, z2, z1, etc. So you will get L1, then you will get L2 at the same point. So you will actually mark it at some other point, somewhere here. Then you will have L3, L4, L5, and finally L6. So this is the way how you can get the coordinate axis, coordinate origins. Okay, so once you have this origin identified, then you identify the assign x-axis. X-axis should be normal to Z0, Z1 and Z0 and away from Z0. So you can assign the x-axis accordingly, and you will get all the coordinate frames as shown here. Okay, so you can identify the coordinate axis. Okay, so once you have this, the next part is to get the DH parameters. So we assume that theta is variable. So for the time being, we don't try to find out the actual value of theta. First, we'll try to find out all the fixed parameters A, D, and alpha. So we can actually have theta 1, and then what will be A1? A1 will be 0. Okay, so this is A, D, and alpha. So A will be 0, D will be this D1, which is 373.4, and alpha is Z0 to Z1. So there is a 90-degree rotation. You have to look at with respect to x1 what is the rotation, and then you will be able to get the alpha. So this way you will be able to get all the parameters. Please get alpha 1, alpha 2, alpha 3. That is more tricky. Others are more straightforward. So what will be alpha 1? Alpha 1? Value 90 or minus 90? Plus 90? Okay. So alpha 1 is basically measured from in Z0 to Z1, measured with respect to which axis? X0 or X1? X1. So which is X1 here? So this is X1. This is X1 axis. So you have to look at from this axis, and then see how much it has rotated. So it has rotated clockwise or anti-clockwise? Clockwise. So it should be minus 90, right? So if you look at from x1, so look at from this. So this is the original position, and it has rotated like this. Okay, so you look at from here, it has actually rotated in the clockwise direction, right? No, I didn't get your question. Once again. x0 to x1. You are talking about x. z0 to z1. z0 to z1 with respect to x1. That is what you need to measure. Okay. Alpha 2, you can cross check your answers later. So find out what is alpha 2. Alpha 2 is z1 to z2. z1 to z2. So z1 was like this, it has actually moved like this. And with respect to x2, so x2 is downwards. Pardon? Plus 90, okay. Find out why it is plus 90. Because if you are looking from here, it is, this was the, okay, this is your x. This is your x, this was your z0. It has moved like this. So it has moved anti-clockwise. Okay. So that is the way how you look at, this was z0 axis. This is your x1. x1 has moved, z0 has become like this in the anti-clockwise direction. Therefore, it is plus 90. Okay. Yeah. Now you have to look at z2 to z1. So z1 was actually, it has moved like this. From this position, it has moved like this, the z-axis, and you have to look from here. So it has moved like this. If you are looking from here, this axis, it has moved like this. Okay. So what will be the angle? Plus 90, right? Again, it is anti-clockwise movement, so you will have plus 90. So this is the way each one you need to check and then see what is the value of alpha. So you have this 90, 90, 0, 0, 90, 0. So that is the way how you get the alpha, because Z2, Z3, Z4 are parallel. That's why you get these two zeros, and then Z4 and Z5 are rotated by 90 degree. Z5 and Z6 are same point, I mean same direction. So it is 0 again. And you apply the rules, then you will get D1, then finally you get D6, and you will get A3 and A4. A2 is 0. So this is actually A3, A4, and this is D1, and this is D6. So you have all the parameters identified, all the DH parameters identified, and once you have this, you need to get the DH matrix or the transformation matrix between each coordinate frame. So you can actually find out what is T10 by substituting the values of theta 1, D1, A1, alpha 1. So you will be getting all the transformation matrices. Only thing you can note down here is that we assumed a home position here. And for this home position, you will be able to find some values for theta. That is, for this home position, you can find a theta value. What is the value? So you will be able to find out theta 1 to theta 6 for the given home position. Okay. Yes, it's a variable. When you change the position, you may get a different theta. But at least for the given position, you will be able to find this theta. So theta 1 is the angle between x0 and x1. You can see there is an angle between x0 and x1, that is 90 degree. Plus or minus, you have to check based on the Z0 axis. So with respect to Z0, you have to look at that this has actually moved. So from here it has moved inside. So it has moved like this. So you need to find out what is the angle of what is the angle theta 1. So that way you will be able to get the home position. So if I call this as the home position of the robot, you will be able to find out the home position theta as 90, minus 90, 90, 0, 90 and 0. So this is the home position theta values. Theta is a variable, but for the given configuration that we are used for getting the coordinate frames, there is an angle between x0 and x1, similarly x1 to x2, etc. So that is given as 90 minus 90, 90, 0, 90, 0. You will be able to, you can verify this later, how you are getting these values 90 minus 90, etc. Why we need this information is that we can actually cross check our forward kinematics by looking at these values. Substituting these values, we can cross check our forward formulation whether you are doing it correctly or not. That is why we need to have this information. Okay. All right. So now let us do the forward relationship. Let us make the forward relationship. So what I will do, I will look at this elbow as the point where we are bifurcating it for the convenience, so that you can actually 3 and 3 joints. So elbow, I will take it as the elbow to base I will first consider, and then tool to elbow, then finally tool to base I can consider. So let us find out this. So if you want to find out elbow to base transformation, so this is T10, this is T21, and this is T32. We simply substituted the values of theta, alpha, A and D into this, and we got this information. Okay, so I did not substitute the value here, but just put it as A3 and D1. Substituted the value of alpha in order to get the matrix. So now if you multiply these 3 matrices, you will get the elbow to base relationship as this. You can cross check later. I am not going to do the multiplication here, but this is somewhere where you normally make mistakes, because either multiplication or substitution you may make some small mistakes, but then before you proceed further you need to cross check whether your formulation is correct or not. If your formulation is wrong here, then the next part also you will make the mistake. You may end up with a completely wrong forward relationship. Yes. Any question? Okay. I mean, as I mentioned, it's not unique, but then you need to make sure that you follow some convention so that it will not be, it will not go wrong. Okay. Okay. So how do you cross check whether your formulation is correct? So what we need to do is to look at the theta values, theta 1, theta 2, theta 3 for the home position. So we took this as the home position. So this is a elbow point we have taken. And now we are actually finding out the base to elbow as the relationship here. Substitute the value of theta 1, theta 2 and theta 3 into this relationship, Px, Py, Pz. So this represents the position of elbow with respect to the base frame. So this is the x position of the elbow, this is the y position of the elbow, and this is the z position of the elbow. Now substitute the value of theta 1, theta 2, that is 90, minus 90 and 90, I think. So substitute the values of theta 1 90, theta 2 90 and theta 2 minus 90 and theta 3 90 into this equation and find out what will be the value of Px. When you substitute value of theta 1, theta 2, theta 3 into this, what will be the value of Px? What do you get as Px? Because theta 1, theta 2, theta 3 90, so this will become 0, this will become 1, right? So you will get Px is equal to A3, right? And then you will get Py equal to 0 and Pz will be, because this will become 0, this will become 0 cos theta 3, therefore this will be D1. So that actually tells you that the position of the elbow with respect to the base frame in the home position is A3 away from the origin of base, which says that this distance is A3. So basically it tells that okay, what you have got the elbow from the base is A3, which is correct. As per the diagram, it is correct. Py is 0 because it is in the xz axis, y coordinate is 0, and your z coordinate is basically D1. Elbow z coordinate is D1, which is correct because as per the home position, we assume this position and elbow is at A3 and D1 in x and z coordinates. So shows that the formulation what you already got is correct. So your angles, whatever the DH parameters you assumed and the coordinate frames you assigned, everything is perfect, and that is why you are actually able to cross check your formulation. So this way you can make sure that your formulation is correct. So whenever you do a forward kinematic relationship, at some point basically in the first 3 joints you do first and cross check whether you are getting it correct and it is as per your home position, then you are able to verify it, and that will tell you that you are correct. Alpha cannot be a variable. No, alpha you cannot vary because once a configuration is given for a robot, alpha normally, unless it is a reconfigurable robot. Okay, we are not talking about a reconfigurable robot. We are talking about an industrial robot which is already designed. You already have a design for it, and you cannot change the joint axis arbitrarily. No. You cannot do that. Z0 is always along the joint axis. Okay, and that joint axis is already fixed for a given configuration. Because you have a motor attached to a joint like this, and you are rotating in this direction only. You cannot say that I will change the motor to this direction. Motor is not going to be changed in a real configuration. So the joint axis is always fixed for a given configuration. Oh, you mean you are saying that why don't you take joint axis along x-axis? Oh, then the whole formulation will be, then you cannot follow this formulation. Then you need to have a different formulation for doing that. No, then you don't call it as DH parameter, because DH parameter says that you assign the joint axis as Z, then you get the parameter, then only we call it as DH parameters, right? So DH parameters has a, because of that formulation only you are telling this is the DH parameters. So if you say that okay, I will assign joint axis by x, y or z, then you cannot say that okay, this is DH parameter. Then this is a different, you need to have a different formulation for doing that. But this is the standard formulation that you can use to get the DH parameters. If you say that on my joint axis is not along z, then no more this formulation is valid. Okay, then you need to have a different way of approaching it. That is complex. That's why a standard formulation has been made. No, it will be more complex. You cannot have that kind of, because then we are becoming arbitrarily assigning joint axis, right? Then you cannot really formulate a standard. No, why x or z? Why not y? No, see, all this assignment comes after the first assumption of z axis. Then if you are saying that is not z axis, then your alpha is not more defined with respect to x axis or z axis. X0, Y0, Z0 is again you can decide what you want to have, which way you want to have, what origin frame. Okay. No. See, no. You should understand one thing. See, theta is a variable. alpha we are defining as the rotational axis, how the rotational axis are oriented. Okay. So, you are saying that you have one rotational axis z, and then how this rotational axis is related to the next rotational axis is basically the alpha. That is how we are defining alpha, the angle between two joint axes. And now you are saying this is z and the next one is x, then you have to define the alpha as between z and x with respect to some other axis. And that will actually makes more complication of the system instead of having a standard formulation. So, this gives you a more standard formulation, then the other one is more arbitrary. So, you do not have any control over the angle, because each one you have to look at which axis you are defining it as the joint axis. Then you have to define that as the alpha. So, this is much more easier. I do not know why you would say that that is more easy. Yeah. So, you are saying between 3 and 1 instead of making 2. No, then why 3? Why not 4? That question will come now. So, why 3? It can be 6 and 1, right? Directly. Probably we can discuss this later. I think we have a different view. So, probably we will discuss it separately. You can meet me and we will discuss it. Okay? Yeah. Okay. So, this is how you cross check. Then you can make sure that whatever the you substituted, you are actually getting it as the 1. So, elbow to base or home position, you can see, so this is your elbow, and so this is A3 and this is D1, and now we know that this position of the elbow is the coordinate of this is A3, 0, D1. So, this way you can cross check your position information, and you can check your orientation also. You will see that the x axis of the third frame or the elbow frame is aligned with the origin frame, origin of x0 of the origin, and therefore, you will see this is 1, 0, 0. The vector is aligned along the same direction, both x axis, so it will be 1, 0, 0. Now, you will see that the y axis of this is the y axis of elbow, and that is along the z0 axis. Okay, so, you have this is 0, 0, 1 here, because y is aligned along the z axis, so it will get this is 0, 0, 1 sliding vector, and then you will see that the z3, that is the z axis of the elbow, is opposite to the y of the origin. Therefore, you will get it as 0, minus 1, 0. So, this way you are sure that your formulation is correct. Whatever the joint angles you assume, the alpha you assume, A3, D3, all the parameters are correct up to this point. There is no problem. So, you can go ahead. So, that is the confirmation that you can have, a cross check you can have with your formulation. Okay. All right. So, now we can do the next 3, that is the tool to elbow. You can find out this transformation again using the same 3 transformation matrices. I mean the similar transformation matrices. We can get this as elbow, tool to elbow as this. So, you find the individual transformation matrix and then multiply the 3 individual transformation matrices, then you get the tool to elbow transformation as this. So, as I mentioned, 4, 5 represents, C4, 5 represents theta 4 plus theta 5, cos theta 4 plus theta 5. Now, again, if you are interested, you can actually cross check this once again, but with respect to this, you have to cross check. You will see that the x coordinate as per this is this one, A4, this is A4 and this is D6. So, you will see A4 plus D6 will be its x coordinate. So, if you substitute the value of theta 4 and theta 5, you will find this as A4 plus D6 and others will be 0, 0, because y and z will be 0 here. So, you will be able to cross check it again substituting the value of theta 4, theta 5 and theta 6. or you can do as a final one. You want to find out, finally you want to find out what is T tool to base. So multiply these two matrices, that is the elbow to base and tool to elbow, multiply, you will be getting it as another 4 by 4 matrix, which gives the position of the tool with respect to base frame. And when you do this, again it's a multiplication of matrices, you will get it as this way. So this is the position vector, just separating the position and orientation. So the position vector will be like this: Px, Py and Pz. This is what you get in the last column of the 4 by 4 matrix, and the other three will be, the orientation will be this one, R matrix will be this. So separately I given. So this is your normal vector, this is the sliding vector, and this is the approach vector, and this is the Px of the tool with respect to base frame, Py of the tool with respect to base frame, and Pz of the tool with respect to base frame. Again you can cross check your formulation, because you have this theta 1 to theta 6 identified for the home position. Substitute the values of theta 1 to theta 6, theta in this case only theta 5, substitute here in this matrix to get the Px, Py, Pz, and check whether you are getting it correctly. So if you do this, if you have done it properly, your Px should be equal to A3 plus A4 plus D6, because that is the x direction length of the manipulator, and your Py should be equal to 0 and Pz should be equal to D1. By substituting the value of theta 1 to theta 6, home position values of theta 1 to theta 6 in this matrix, if you are getting this as the relationship, that means you have done it properly and your formulation is correct. If you have not done it, if you are not getting it, that means something is wrong with your formulation. Either the joint angle taken for the home position, or the alpha you taken, or the origin that you assumed, there may be something wrong. That is a cross check that you can do to make sure that your formulation is correct. Okay, so if you want to cross check, you can cross check it here, and you will get this as A3 plus A4 plus D6, 0 and D1. So you can see that this is A3 plus A4 plus D6, the x coordinate with respect to base frame of the tool, and the z coordinate with respect to this is D6. So your formulation is correct, and therefore whatever the parameters you assumed and whatever the parameters you calculated, everything is correct. You want to have one more cross check, you can check the orientation of the tool frame. So this is the tool frame. How this tool frame is oriented with respect to the base frame can be cross checked, and you will see that this z axis is aligned with the x axis, and therefore you will see this is 0, 0, 1, and x axis is aligned with the z axis, and therefore you will see it is 1, 0, 0, and then this is y axis is along the y of this negative y, so you will see 0, minus 1, 0. So your formulation is correct, you have got the forward kinematics correctly. So that is the checking that you can do when you are doing a forward kinematic analysis of any manipulator. Whatever may be the manipulator configuration, assume a home position, and then for that home position you assign the coordinate frame, get the DH parameters, find out the home position theta, and then substitute this in the forward formulation up to the wrist or up to the tool, and then cross check, and finally make sure that what you are getting is correct. If you are not getting it correctly, something has gone wrong. That is the final. Then you can go check and then find out what has gone wrong. Okay, any questions on the forward kinematics? So we will not be doing any more examples for forward kinematics. We will be moving to the inverse problem now. Okay, fine. So two things. One is about a tutorial tomorrow. So there are two questions from the previous tutorial which you could not complete. And along with that, you will be doing this also in the next class. That is tomorrow, 9 o'clock, 8 o'clock. You will be doing the forward kinematics of this, and then trying to verify your answers with the soft composition values. So it's again a simple manipulator, which we have done it in different ways. So no complications. We can get it straightforward. So try to do this and then submit the answers in the next class. So this is your position, what you are interested, tool position. You need to find out the tool to base matrix as a 4x4 matrix and get the Px, Py and Pz as a function of the DH parameters. So this will be done tomorrow in the class. So please come prepared. Don't say I did not get enough time to do it. Tutorial will help you to solve it, but you should come prepared with the basic things that we have already discussed in the class. Okay. So there will be an assignment given to you. Okay. So the assignment will be, the questions will be released by today or tomorrow. You have to submit by next Wednesday. Next Wednesday is 18th or so. Basically, there is one problem on the forward kinematics of an industrial manipulator, and then the second one will be a coding problem. So you have to write a code for the forward kinematics of any manipulator, a general code. Basically, how do you get the DH parameters? I mean, once the DH parameters are given to you, how do you actually find out how do you write a code for the forward kinematics and then getting the position? Yeah. Pardon? You can use, don't use MATLAB, any other software can be done. Okay. MATLAB will be the easiest thing to do. I don't want you to write it in MATLAB. So you can write it, Python or any other language. So finally, you have to use that one for a standard manipulator and then show the results also using the code. How do you get the results? So basically, that is one which will help you to find out the workspace of a manipulator. Once you substitute the value of theta, for any value of theta, you should be able to get the position and orientation of the tooltip. So by sweeping the joint angles, you will get all the points that the robot can reach. Then you will get that as a workspace of the robot. Okay. So questions will be released by tomorrow. You have to submit the result, the answers in Moodle by 18th. Okay. So just to test how much you have understood whatever that we discussed in the last few classes, there are a few questions for you. You have to answer these questions. When the arm of a robot has one revolute and two prismatic joints, its workspace will be fast. RPP, cylindrical, right? Yeah, should not think this much. If the axis used to orient the tool intersect at a point, then the robot is said to have kind of wrist. What kind of a wrist? They are intersecting at one point. All the joint axes are intersecting at one point. Then you call it as spherical wrist, right? So it's known as a spherical wrist. What will be the y-axis? Downward? Correct? Okay. T is a homogeneous transformation matrix. Okay, so T is basically R. If this is T, what is T inverse? R transpose minus R transpose P, right? So that is the inverse of this matrix. What is alpha, or how is alpha defined? Alpha is defined as the angle between Zk and Zk minus 1 measured with respect to x, k. Okay, so that is the alpha. So now you know theta, what is A, D and etc. What are the joint parameters? theta and D. Link parameter A and alpha. Okay. Okay, so you know all the answers. So we'll have an assignment. So question will be available. So this 19th March, I am not sure. Yeah, 19th March is Thursday, right? So we'll make it on 18th March. Yeah, 19th your exam starts, so I don't want to do it during. So probably 18th we can finish it. 18th March you have to submit. I'll assign this. Okay, so I thought of starting inverse problem today, but I think we don't have much time. So what we are trying to do is, so far what we did was to see if you know the joint parameters theta, what is the P that you can reach is the forward problem. That is, if you have a manipulator and if I know these values of theta 1 to theta 6, I know where this tool will reach. That is basically the forward problem. So I can actually command the joint angle and move it to a particular position. So that is what we know when we command some joint angles, we know where this will reach. So we can find out the position. But most of the problems in industrial robots is not that one. I have a workpiece here. I want the robot to go and pick up this workpiece. And I know where the workpiece is at present. So what I know is that there is a workpiece here. And I know the position and orientation of this workpiece. I want to know what should be these joint angles to reach this position. So what should be this? What should be the joint angles to reach this position so that the robot can pick up the object? So the object position and orientation is known. I want to calculate what should be my joint angles to reach here. That is basically the important problem in industrial robots, or most of the industrial problems are like that. Where the robot reaches is not that critical, but how can I reach an object and pick up the object? Or if I want to place this object here, I know where to place the object with respect to the base of the robot. I know where to place the object, but then to place this object here, what should be the joint angle to reach there? That is what I don't know. So this problem of getting theta, if the P is known as the inverse problem. So the forward problem was theta is known, what is P is the forward problem, but then P is known, theta is not known is an inverse problem. And this is much more complex compared to the forward. So forward now appears to be more straightforward. If you have standard formulation, you just apply the standard formulation, you get an inverse solution. Forward problem solved. But for inverse, there is no standard solutions. Each robot has to have its own inverse solution. There is no standard formulation like a forward problem. You have to look at the forward of the particular manipulator and then see how to solve for the inverse. So it becomes much more complex. And another problem is that if suppose there is an object here and I want to reach the object, I can calculate joint angles to reach here. But I can actually reach like this also. So I have two ways to access this, or sometimes multiple ways to access this. Then it becomes more complex because I will have multiple solutions. So how do I actually tackle the multiple solutions as well as the manipulator specific solution for the inverse is the challenge, and therefore the inverse problem is complex or much more complex than the forward problem, and there is no standard formulation like DH in this case. You will be using DH to solve it, but there is no standard way to solve all the robots with the same kind of a solution. Forward we have the same solution for all kinds of robots, whether it is 5-axis, 6-axis or any configuration, you can use the same DH formulation and get the solution. But inverse, that is not possible. You need to have manipulator specific solutions to solve the inverse problem. So we will discuss this in the next class, and then we will talk about velocity relationship also later. Okay, so we will stop here. So come prepared for the tutorial tomorrow and check your Moodle for the questions on assignment questions. Thank you.